So it took some, so there we go, I started again. It took some work. It was a very self-conscious effort for me to stop starting lessons with the word so. So, today we're going to start by going through the warm-up, which is evaluating this interval. You had a hint, let x equal sine theta. So, I'm going to go ahead and just put up the solution. So, if x is sine theta, your dx is cosine theta d theta. What you do is you write, it's okay, it's okay. Replace your x with a sine theta. So you end up with square root of 1 minus sine squared, right? And then of course your dx becomes cosine theta d theta. What is this? Oh, y'all know. What is the square root of 1 minus sine squared? Or what is 1 minus sine squared equal? Cosine squared, right? So into the square root of cosine squared. Now, normally you can't assume that the square root of cosine squared is cosine, but for this problem you can, and the only reason that you can is because it's told at the beginning to let theta be in this interval, right? If theta is in this interval, that means cosine is positive, and therefore the square root of cosine squared is equal to cosine. All right, so what we end up with is cosine times cosine, which is cosine squared. How do we do an integral? And it's already up there, but that's okay. I'm still going to pretend it's not. How do we do the integral of cosine squared? Which identity? That reduction, yeah, that reduction identity, which is, it's really the double angle identity for cosine kind of reconfigured, right? So you have to do a power reduction on cosine for this one. So, and you thought they were going away, and they're not. Isn't that great? Right? More review. So you do that power reduction, you end up with the integral of this. And now you can just jump to the answer, or not. So here, the antiderivative of a half is 1/2 theta, right? And the antiderivative of 1/2 cosine 2 theta, well, the antiderivative of cosine 2 theta would be 1/2 sine 2 theta, right? But then you have times another half, so you get 1/4 sine 2 theta. Now you feel like you're done. Are you done?
No.
No, why not? Oh, that was so good. Yeah, no one in my first period said that. So, very good. Yeah. So, here's the problem. The original function is written in terms of x, right? So we have to have our answer be in terms of x. So, how do we make our answer be in terms of x? So, we go back up here and we say, well, let's see. If x equals sine theta, that means that theta equals what? Arc sine x. So if we go back to our answer and replace the theta with arc sine x, here's what happens. And you know, I'm going to walk you through the next example. For now, this one actually just becomes an arc sine x, and then this one we would have, to use a geometric shape to help us manipulate it. Anyone know what that shape is? Triangle, right? When you have to simplify those trig functions, you end up with that. I actually took the sine 2 theta, replaced it with 2 sine theta cosine theta to make the triangle a little bit easier, and then did it that way. So, otherwise it makes it very confusing when you have to double the integral. Yeah, so fun. Right. I sure can.
How did you do the triangle?
All right, let me show you real quick. I was going to show you. You might as well just start now, right? So, all right, so theta is arc sine x. So what we want here, I'm just going to ignore that and just work on this one. So what we're looking for is we're looking for the sine of the arc sine of x times the cosine of the arc sine of x, right? Okay, what is the sine of the arc sine of x equal to? That's just x, right? So this part, that's an x. That's still an x. Let's pretend it's an x. That's an x, right? So that's where the x comes from. So really all we have to do is the cosine of the arc sine of x. So we draw a triangle. You learned how to do these triangles way back when you were learning the derivatives of the inverse trig functions. It's been a while, right? So you let this angle be theta, and you say, all right, theta is the angle whose sine is x, right? So if our sine is x, that means opposite over hypotenuse is x over 1, so we can label the sides x over 1. By Pythagorean theorem, this side then becomes 1 minus x squared. And now what do we want? We want the cosine of the angle whose sine is x. Cosine would be adjacent over hypotenuse, so you end up with that root 1 minus x squared. Yeah, fun. All right, let's try one for real. First, let's talk about what we're doing today. Trig substitution, woo-hoo! Okay, so today we're going to evaluate integrals involving 3 cases of radical functions using trig identities. Here we go. So, we are today learning how to evaluate 3 more families of integrals. And it's actually 3 larger families than you think. Now, many of the problems we're going to do today don't have to be done with trig substitution. Some of them can just be done with straight up u substitution. It's just another method, right? Some problems require trig substitution. Some problems it's just another method you can use if you need another method to use, right? So it's really just kind of adding one more little strategy to our arsenal of how to attack integrals, right? So here we go. We have 3 cases. So you can do this whenever you have a root of number minus x squared, or u squared here, right? Number squared plus x squared, or x squared minus number squared. If you look carefully, when you have number minus x squared, you're going to use sine. Number plus x squared, you use tan, and x squared minus number, you use secant. These should look mildly familiar. The fact that we're using sine, tangent, and secant, and the fact that the one that we use, how it relates to what's under that radical sign, should feel at least somewhat familiar. So I don't have any idea of where we've seen it before, where we had like number squared minus u squared and related it with sine. Of what? Arc! Yes, arc! Okay. Yes, the integrals of all the inverse trig functions and the derivatives of all the inverse trig functions. Because it's not really the integrals of the inverse trig, it's really the integrals of these where the answers were inverse trig, right? But yeah, the derivatives of all the inverse trig functions have the same type of setup. They may not necessarily have a radical, right? Tangent doesn't have a radical, but it's still an x squared plus number squared, right? So anyway, they still kind of associate with those arc trig derivatives, inverse trig derivatives. All right, so anyway, so kind of make a note of what to do for each one, and I will walk you through some problems, and then you will do some problems. everyone good? Oh. Okay. Okay, let's walk through one together. So we're gonna walk through this one. Doesn't look anything like the three cases we just saw, right? And that's okay, you're really just focusing on the radical to make your decision on what to substitute. So for the radical, we have root 9 minus x squared. Do you know which trig function we should use for this? Is it secant? Is it sine? Are you sure? Are you positive? Yes. Okay. Yes, it's sine, because you have number minus x squared, right? If it's x squared minus number, then it'd be secant. Number minus x squared is sine. All right, so we're going to let x equal, all right, so x is going to equal a sine theta. What is a?
3.
Is it 9 or is it 3?
3.
It's 3, right? Because this right here, that's a squared, right? So our a is 3. So we let x equal 3 sine theta. All right. Another end's going to be I need to line up the board. Sine theta. Okay, so now our dx. What's dx? I'll start. It's 3. Cosine theta, d theta. Beautiful. Yes. 3 cosine theta, d theta. All right, so let's rewrite our integral. Okay, so dx is 3 cosine theta d theta. I'm going to put the 3 cosine theta on top, and I'm going to put the d theta out to the side. D theta. All right, so here we have an x squared. What is x squared going to equal? What is it? 9 sine squared, right. So we have 9 sine squared, square root of 9 minus x squared, which is 9 sine squared. This is the reason you do a sine theta and not just sine theta. You do a sine theta so that you'll have an a squared and an a squared in each term, and then you can pull it out, right? Because you want to be left with a 1 minus sine squared so you can convert it. So you need that a in both terms so you can factor it out. So for our next term, so we have, if I pull a root 9 out, pull a 9 out of each term, and so we pull a root 9 out, it becomes a 3. So we have 9, I'm just going to rewrite, 9 sine squared theta times 3 root 1 minus sine squared. Good. All right, so what does 1 minus sine squared equal? Oh, this is leftover from the last presentation that didn't get deleted. All right, so we have integral 3 cosine theta over 27 sine squared theta, and then we have, this is going to be the square root of cosine squared, which is just going to be cosine. What's that? Magic? Next we do magic, or we've already done magic? Oh, yeah, isn't that nice? Yeah. So now you can cancel the cosines, right? So, goodbye, cosine. There's one other little thing we can cancel, just to clean it up. What else can we cancel? We can cancel 3, right? So end up with 1 over 9 sine squared theta. Integrate 1 over sine squared. What can we we do? Cosecant squared. Very good. So we end up with the integral of 1/9 cosecant squared theta d theta. Oh, well, now we're going to have to know the antiderivative of cosecant squared. What is it? Are we sure?
Negative, something else.
What is it? Are you sure? Is that a question or?
Negative cosine.
Yes, it is. See? Good. All right, yes, it's negative cosine. So I end up with negative 1/9 cotan theta plus c. And then we're done?
No.
What? Why not? We gotta go back and write in terms of x, right? Okay, so to write it in terms of x, we go back up to the top and say, all right, if x is 3 sine theta, that means that theta is what? Close. It's not 1/3 arc sine because you have to divide by 3 after you do the arc sine or before? You gotta do it before. So it's actually, yes, it's actually arc sine of x over 3. Yes, very good. All right, so if we replace all of our thetas with arc sine x over 3, so this is negative 1/9 cotan arc sine x over 3 plus c, and can we leave it like that in terms of x? Yeah, you can't, they won't let you. So, yeah, it's got to be in its most simplified trig form. So if it's trig form, it's got to be as simplified as possible, and if it can be written in algebraic form, then that's what you have to do, and this can be written in algebraic form. So what are we going to have to draw? A triangle. So we draw a triangle. Label an angle theta. Theta is the angle whose sine is x over 3, right? So sine is opposite over hypotenuse, so we label x over 3. Now we need this side. So Pythagoras says this side is equal to, right, square root of 9 minus x squared. So our final answer, we want the cotangent of this. Cotangent is what over what? Adjacent over opposites. So we end up with root 9 minus x squared over x. So root 9 minus x squared over x plus c. And we don't even have to change our constant because c didn't change. We didn't change anything, we just rewrote in a different form. So the c is this. So there you go. Beautiful. All right, you ready to try one? Good. All right, give this one a try. Just a word of advice, before you do anything else, personally, I would pull a root 3 out in front of the integral, a 1 over root 3, to start with, so that you don't have to mess with a u substitution on the 3x squared. Yes, you could. But we're going to do trig sub, because we're learning a wonderful new method, right? Well, yeah, but it's that cool, right? So, yes, you could, honestly, you could do this problem with just straight up u sub. But we're going to do trig sub, right? Because it's fun and we're learning something new, right? It's time to grow our brains. What I would do before starting is, that's the first thing I would do, is pull that 1 over root 3 out. Which function, oh yeah, u is x, yeah. Which function would you pick for x for this one?
I don't know.
Arctan. Arctan. Or not arctan, just tan. Sorry, a tan.
second one.
Oh, you know, it's just, the book wants you to just memorize how to go from here to here. It's doing a bunch of steps. I personally just walk through the steps each time. So, because if U is a sine theta, then you end up with pulling out a root a squared in both terms. So you get a times 1 minus sine squared, which is cosine squared, which is root cosine squared, which is cosine. So you end up knowing that root a squared is squared is just a cosine theta. But I personally have a hard time memorizing. So since you're stuck with me, you have to walk through it every time. Yeah, you could.
How would it have helped?
Did you get dx equals 2 secant squared?
You could have just skipped this, yeah, you would have skipped from here to here. Yeah, you would have skipped a couple steps.
What if there's the?
That's what the A is, that's your A squared. That's taken into account in the formula. I'm just not a good memorizer. I know I can remember this because this reminds me of my art, my first trick. I can't remember that.
Oh, okay.
So, yeah, but if you can, go for it. Okay. Absolutely.
So if you did the way where you're memorizing it for this problem, would you go?
I would still pull a root 3 out.
Would you still have the 2 tangent theta on top and then have a secant theta on bottom?
Yes.
Is this still there? Or yes.
Oh, okay.
Yes. Yes. I'm thinking correctly.
So it's x squared plus 4.
Oh, secant, you would have, yes, well, you'd have the tan plus, you'd have to make sure you do a d, you convert your dx as well. Right, that's important too.
Oh, so when you put the 2 tangent in.
Make sure you don't ignore the dx. The dx is important, significant, plays a big role in this one.
Well, when you square.
Oh, you're right.
Right, not just the theta. So you get, and then that way you can pull that root 4 out, and then you can apply your idea.
So you have one over 3 times the only one.
Yep. Yeah, and then you know what that equals.
I think it's 2 things.
Yeah, and isn't it funny that no one in first, oh no, don't do this now. It's funny that no one in my first period asked me about this, so I kind of glossed over it. But, so in this class, several people are asking me about this little statement there. So it's basically what you end up with when you plug the a sine theta in and do all your manipulations, right? So if you can memorize that this equals this, you actually get to skip a few steps. You just have to be very careful how you do it, right? Like if you went ahead and did it, right? If we said, all right, so this is the square root of a squared minus a squared sine squared, right? We plugged in our u, and then pull out the a, so you get the square root of 1 minus sine squared, which is the square root of cosine squared, which is cosine, right? So what this does is it kind of jumps from here through all the steps to here. And if you want to memorize that square root of a squared minus u squared equals a cosine theta, you still have to make sure that you let u equal a sine theta because you have to find du, right? You have to find your dx, and you have to make sure that you rewrite all the x's. But yeah, so, but that, you can do that. If you want to memorize, you can. It'll save you 2 steps.
Oh, wait, could you
for you, is it still listed?
Yes, I'm gonna go ahead and put up this portion
This?
of the solution. Okay, be careful, you gotta write the dx, and then you gotta plug in your dx, because that changes. Oh, you put it in here, okay. Make sure you feel like, is there a find your report, like, don't be. I did that. Oh, yeah, got it. Oh, you've already jumped into the answer. Yes. You are very lazy with your writing. It's so beautifully written, it looks so nice that it doesn't look like you get any laziness here. But you have to be very intentional with your DXs, right? And then there's gonna there.
So we have the same.
Right.
Where's your theta? Where's your theta?
So yeah, mine's
Tangent of that, theta, this theta.
How you doing so far?
Oh,
Fantastic.
Bedroom, are you past this stuff?
so that's x squared plus 4.
So did everyone get to a 2 over root 3 secant theta plus c? Yes? No? We have to keep going, but. All right, let me come over and look. Everyone else, once you get there and draw your triangle, you should end up with that. Ah, okay.
I was like, sorry.
You have to be very meticulous and intentional with your dx and your d theta replacement, right? You have to be very, very meticulous with it. So many, I don't know about Mr. Thomas or his students, but I know with my students, so many of you do not write the dx when you write your integrals, and it's really important. Look at what dx was here. It wasn't just d theta, it was 2 secant squared d theta, and if you didn't have that, your problem was probably just a mess, right? So be very careful that you write the dx where it belongs, that you write the d theta where it belongs, and then that you write your plus c at the beginning, like on the first line when you take that antiderivative, and you carry it through. I see puzzled faces. Yes?
Can you do the last step where you go from 2 over 3 secant theta?
Oh, here to here?
Yeah.
Okay, yeah, let's do a triangle. Okay, so, let's see, what does x equal? Oh, x is 2 tan theta, which means theta equals arc tan x over 2? Does that make sense? Okay, so theta is arc tan x over 2, so I'm going to replace this with 2 over root 3 times the secant of the arctan of x over 2. And then if I draw a triangle, so tangent, opposite over adjacent, x over 2, square root of x squared plus 4. So then my secant is hypotenuse over adjacent, so it's root x squared plus 4 over 2, or 4, I have 4 plus x squared. But anyway, 4 plus x squared over 2, right, and then the 2's cancel. How's that sit? Sit okay? Good, let's try another one. Okay, all right, good. 1 over square root of x squared minus 16. Well, there's this one there's another one, and then there's a BC free response practice problem. God, we'll have plenty of time because we still have a half hour after lunch and you have no homework questions, right? Yeah. Class is not done just because we go to lunch, right?
Divide by
Because the X comes first. Yep. Hello, gentlemen. How are you guys doing? I'm going to have fun grading your work.
You graded an
I
A.
can already tell. Okay. It's like doing a decoder kind of thing.
How can you tell if you graded an
Right.
A? You have to have a plug.
Did you know that right? Would be a doctor, right? Don't doctors have some terrible
Yeah.
there you go. It's okay. You guys doing okay? What are you guys doing? Oh, yeah, good try, but our secret could have next time, right?
Okay. So if you do it with this method, for this one,
Yes.
if you it has the use graded an A. So
Yeah, I always ignore that and just do the problem.
No, but like,
how do you know if you use graded an A?
I don't know. That's why I just do my way. And I'm happy. I'll let Mr. Thomas do my lunch.
Miss Price, if you're doing something and I'm like really good joke, I just like whisper it above the camera. That way,
You
like,
can
I
tell
won't
the whole
disrupt-
class if you
No,
want.
that way I won't disrupt the time, but like, you break the whole, I love it.
I'll call it during your time. If you want to joke on camera, why don't we wait until the end of the lesson and then you can tell a joke? You can tell a joke every day if you want. You can do like the daily joke.
No,
daily jokes?
yeah, that's all related though, like,
Do you have a joke related to this?
no, not yet, but like, if you're saying something and I'm like,
Alright, ready?
Well, then say it when you got it. It's okay.
Who's the math teacher?
How?
7.
That worked, actually.
You worked.
Yeah, that was pretty good. That was pretty good. I like it.
Integral, the secant of that would be.
Oh, it's just
Arc secant.
What is integral of?
Yeah?
we can't do that.
For which one are we doing?
What?
Sure. Oh, like does arc secant, is that a valid function? Absolutely. There's an arc for any trig function. There's an arc function. Yes, absolutely. Very good question. Oh, what?
Okay.
Yeah. Ooh, what is the integral of secant? No, it's got a log in it.
Natural log of secant, actual value of secant theta plus tangent theta.
Very nice. Very nice.
Is that positive?
Is it positive?
It's positive.
No.
I didn't do that.
How are you guys doing on it? Did y'all get down to integral of secant? Yes? Uh-oh. Close for it.
Excuse me, please.
Where's your?
Yeah.
Replace the X with this, yep. That's good. If you're doing it repeatedly, it means it's something that you know you need to work on.
That means it's 4 times.
This answer is fine, but I will tell you, if this is a multiple choice question, and it would be, that would be the answer on the exam.
Why can you just get rid of the four?
Just before I explain how to get rid of the 4s, are there any questions apart from the 4s?
On the bottom, you can have one.
Right? It's math, may the 4s be with you. Okay, yes, Justine?
Can you do the triangle thing?
I sure can, okay. So, we know that x is 4 secant, right? So, theta equals arc secant x over 4. Okay, so what we have then is the natural log of the secant of the arc secant of x over 4. So when you have a secant of an arc secant, it's just, they kind of undo each other because they're inverse functions, so you're just left with x over 4 for that part.
Okay.
So let's just work on the tangent. So you have tangent of the arc secant of x over 4. So we draw a triangle. This is the angle whose secant is x over 4. Secant is hypotenuse over adjacent. So by Pythagorean theorem, this is the square root of x squared minus 4 squared. Right? So then your tangent would be opposite over adjacent. So root x squared minus 16 over 4.
Yeah.
All right, so if you're wondering how to get rid of the 4s, let's just review our natural logs, right? So this is the same thing as natural log of the absolute value of 1/4 times x plus root x squared minus 16, right? Yes, no? Where is that okay?
Yeah.
Oh, okay, you looked very puzzled.
No.
Okay. Not really puzzled, maybe skeptical.
Okay.
Okay, all right. So now, remember, when we have a natural log of this times this, that equals ln 1/4 plus ln absolute x plus root x squared minus 16, right? Whenever there are constants, any kind of constants, they all get lumped into the C. Now, technically, this is wrong, right? We should have a, something like that to know that they're different constants, right? But yeah, all constants get absorbed into the unknown constant on the exam. Okay, good. One more time. And then we're going to do this, and then when we come back from lunch, we will do a BC review problem. So this is 1 over the quantity x squared plus 3 to the 3/2 power. I'm going to give you a little hint on how to start it. We need that root, right? So think of this as that. Yes, it would. Beautiful. Yeah, it's okay for A to be a root. A will be a root in this one.
You gotta say here, so you can square it over. Oh. Oh, okay. So it's just one over.
Squared, square root cubed. So you end up with secant cubed. So secant squared or secant cubed. Yep, 1 over secant, which is this one. Yeah, very good. Yeah. Okay, so you got it. So your integral, so you got sine, and then that's in terms of theta, so you have to rewrite the theta in terms of x. Oh, okay, so what is your original x? Where's your x? Where did you first write it? I see it. That's right, x equals. No, it's this. That's a different problem. Root 3 tan theta. So solve this for theta. So it'll be arctan x over root 3. No, now that's your theta. You have to take the sign of that. Now you gotta do it right.
Have 3 plus x squared.
Give it a shot. You can do it.
Check like the circle, the triangle.
Is there some little bit?
No.
Okay, so I have 1 over 1.
Alright, do it.
Yeah, it's because you have to cube the root 3, because it's in here, it's being cubed. Yeah, you end up with just 1/3 out front, because almost everyone forgets that when they pull the root 3, it's still being cubed, right? So it's root 3 over root 3 cubed, which is 1/3. Yep.
You got it right.
So then we need to make it.
Hated all this.
Oh, pencils down, huh?
That's great. Last one.
Why?
Alright, so right here, let's just start.
You don't.
1 over 3 root 3 integral of 3 secant square theta d
So
theta.
you're trying to do a double root, but there's just one.
Theta equals square root.
So it's just root 3, and then, so you have, and then be careful because everything that's there is missing.
It's not.
So you're gonna have to, then you pull the root 3 out, you have to cube it. So you end up with root 3 over.
How do we know what u is?
So X.
Is 1 over
I'll write it out. Oh, like, is this spot on? Yes, this is 3 to the 1 half.
Give you the problem, I can give you the answer, but I can't really explain it.
That's what the first day is always.
X over root 3.
Got it. Very good. Good. Anyone else need some help?
Yeah, oh, you have a book?
Yeah, I'm sorry, what was that?
I didn't say anything.
All right. We still got 6 minutes. Fantastic. So, 2001, number 5 on the BC calculus exam. We're going to do the whole problem. Now, part A is a topic we have not learned yet. We will learn it at the end of this unit, so we've got a couple weeks before we get to this. But I think you guys can figure out part A without me teaching you anything. So I think you can. If you don't get it, that's okay. But I think you can figure it out. If you kind of like, maybe this is this and this is this, and you kind of try to figure it out, you'll probably get it. All right? So it says, let f be the function where f prime equals negative 3x times f of x. For all real numbers x, where f of 1 is 4, and the limit as x approaches infinity of f of x is 0. Part A, evaluate the integral from 1 to infinity of negative 3x f of x. Show the work that leads to your answer. Part B, hey, Euler's method. Let's see what you remember from yesterday, right? Start at x equals 1, with a step size of a half, get to x equals 2. Right? So 2 iterations of Euler's method. And then part C, solve the differential equation dy dx equals negative 3xy using the initial condition f of 1 equals 4. So, there we go. Get started.
I go from 1 to infinity of f prime, but
Yeah.
so it'll just be
It's either approaching I thought it was. I don't know if it is.
wait, this twice?
Yeah, but you know, like half of beer, like more beer. Okay, did you get an answer? They all add up to 2. That was 0.
Yes, you got it. I just want
What's the second fundamental theorem?
That's the derivative of the integral with variables in the limits. But that's not a variable and we don't want the derivative.
So, but I know what it is.
You do know what it is. Yes.
Also follow the question.
In 3 minutes. Yes, you got it. Fantastic. Yeah, good job.
So this is the integral of the
Yeah, we don't know what it is. I got it, Kate.
I'm gonna, don't worry, I'll have the problem still up. But I am gonna show you. So the first answer, if you figured it out, was -4. So well done.